Okay, so we start. We start right.
Yeah, sounds
Okay. Good morning. Good afternoon. Okay. Here is the LSST working group. Yeah. Due to the time zones, you can see some people in America or in Chile they cannot attend, but they will catch the recording. Because the time zones is only friendly for the China and for the European and also or sometimes Australia, with Australia. Okay, this workshop is about the near field cosmology and anything related, and we will know the first look of the LSST has just appeared last month. So this is an exciting news for all the community. Yeah, to the near field cosmology, to the open clusters, to the global clusters, to the stars, to the galaxy. Yeah, everyone is excited about this. So we created this group to make some communication and make some to exchange ideas and exchange your thoughts and your about your projects and anything else to um, to be here. So yeah, today we are very happy to have the Danny Horta. Yeah, Danny Horta is a postdoctorate in the Institute of Astronomy and is the University of the Edinburgh in UK. And before that, he was a Flatiron Research Fellow and is a Center of Computational Astrophysics in New York. And he obtained his PhD from Liverpool John Moores University. Yeah, his research in interrace concern galaxy formation, especially understanding the formation and evolution of galaxies, and by statistically modeling large-scale stellar survey data of the Milky Way and the local group. Okay, take away.
thank you, Haifeng. I'm going to share my screen here really quick,
Mm,
and just give me a nod that you can see that.
mm,
Yeah, okay, great.
mm.
So yeah, thank you very much for having me today. As Haifeng said, my name is Dani Horta, and I am a Marie Curie Research Fellow at the University of Edinburgh in Scotland. Um, I've had the pleasure to give many talks about the understanding the assembly history of the galaxy, and this is the topic that I'd like to discuss with you today. But I think it'd be really nice, given that it's a working group, and we're all thinking about similar questions, but in different ways. That if you want to ask a question or have a thought halfway through the talk, please just shout out, and we can discuss a little bit. So I'd like to make this as informally formal as possible. So as I mentioned, I want to talk to you today about some ideas and some thoughts on how we can reconstruct the mass assembly history of the Milky Way, and from that, trying to understand how galaxies form and evolve in the universe. So in our current best model for cosmology, lambda CDM, we know that galaxies grow in great measure via this process of mass hierarchical assembly. And by this I mean that you have in the early universe halos and the stars and the baryons within them coalescing with each other and merging onto larger mass halos, and as a result, these systems grow in size over time. And to illustrate how the baryonic components of these, so the galaxies within them, undergo this similar process, here's a video from cosmological simulations. So specifically, these are the FIRE cosmological simulations, showing you how a Milky Way mass galaxy evolves from the start of the universe to present day. As you can see, this build-up of small clumps is a pivotal mechanism that drives formation of galaxies, especially in the early phases of the universe. So we really need to try and pin this down if we want to understand how galaxies form. And actually, this process we can now see with our own eyes, thanks to amazing telescopes that we have. So here's an example of Stefan's quintet from JWST. This was one of the initial images they released, showing 5 galaxies where 4 of these are interacting with each other. And it's essentially showing you this mass hierarchical assembly of galaxies happening in the real universe. Now, during this process of mass hierarchical assembly, as you know, the debris from these smaller mass building blocks that have been donated to the larger mass system in order to grow in size are typically deposited in the component referred to as the stellar halo. So therefore, if you want to understand this process, you need to go hunting for the stellar halos of galaxies. Because the stars and the components in the stellar halo are what are going to allow you to unravel the accretion history or the assembly history of that galaxy. Now, for the Milky Way, the stellar halo is a small amount of mass relative to the disk and other components, so it only amounts to approximately 1% of the total stellar mass. But I think, as I mentioned, it is a treasure trove because it has the debris from all these different building blocks, and it really allows you to understand the sort of family tree of the Milky Way. Now, if you were to do this sort of analysis in external galaxies, so for example, if you were to point a telescope at Andromeda or Centaurus A, two of the closest spiral galaxies to the Milky Way, you would find that you could observe large regions of its stellar halo. However, the detailed properties and the detailed structure would be very difficult to infer. And this is because you just don't have the power to resolve stars individually in large numbers compared to the Milky Way. However, this might change now that we have LSST, by the way. So I don't know how this will change. You can tell me better. But until now, at least, this is sort of the picture that you have for external galaxies. And while it's not as unprecedented as the Milky Way, I think it's still really interesting if you want to study like general properties of stellar halos. So say if you want to understand how many shells or how many massive streams they have, which can of course tell you about the accretion history, but also model the density or the luminosity function as a function of projected radius to very large scales. You can do this in external galaxies. But if you want to look at the intricate details of the stellar halo component and try to figure out where these stars came from and where those stars came from, and from that understand how the galaxy assembled, you really have to restrict yourself to our own galaxy, the Milky Way. And this is thanks to the large push and advent of large-scale stellar surveys. So I can see we have a question here. No, it's not a question. So these surveys have provided the necessary data in the form of astrometry, photometry, and spectroscopy that allow you to really piece together the origin of different stellar populations in the stellar halo of the Milky Way. Now, from that, we've learned a lot of things. We've learned that there are a lot of kinematically cold systems, like the bunch of stellar streams. We know that there's infalling satellites, like the Sagittarius Spheroidal or the LMC and SMC. And we have this beautiful field of streams view as provided by this image from either Bilocuro Fitalo or by Anna Bonaccia. However, if you want to really understand the earliest phases of assembly, you really need the data, and specifically chemical abundance data in combination with astrometric data in order to disentangle phase mix debris. And this was largely been driven thanks to the advent of Gaia and complementary ground-based spectroscopic surveys like Apogee or Galar or LAMOST or RAVE, etc., which has allowed us to really piece together different building blocks of the Milky Way. And this has led to a flurry of discoveries, particularly thanks to Gaia DR2, and particularly in regions close to the solar neighborhood. So one of the main discoveries was this Gaia-Enceladus sausage debris, which we think is the debris of a major accretion event that occurred about 8 to 10 years ago. But of course, there's been a bunch of others. And one that I'd like to highlight is one that was actually found in the innermost regions of the galaxy. So this is within 5 kpc, which are debris of the stellar population that our group in Liverpool identified, which we think are debris from a major building block as well, but very early on in the Milky Way's life. And this is the Heracles debris. But as I was mentioning, one of the major discoveries was, or not discoveries, I guess it's more like a cemented result, was that there's a large population of stellar halo stars that appear very radial in their orbits and have chemical abundances which are typical of dwarf galaxies, and we think come from this massive and ancient accretion event. And we think that this Gaia-Enceladus or Gaia sausage debris dominates the local stellar halo, so anywhere between 5 to 30 kpc. And this is just a summary of different results that kind of hinted at the same thing. Now, the reason why this was such I think, an interesting result was that because it kind of helped explain a lot of results that we previously found and were trying to understand. So for example, there's been overdensities identified, like the Virgo overdensity or the Hercules Aquila cloud, which are these pileups and overdensities of stellar halo stars, which have been linked to the debris of the Gaia Enceladus sausage. So we think that these are just points in the debris in which the orbits reach apocenter, and because of the dynamical timescales, they pile up there, and then they form these overdensities. Now, because of this, people that have been modeling the density profile of the stellar halo in the Milky Way have found that actually it appears broken. And by this I mean that around 15 to 20 kbc, you have this break in the density. And actually, this we think now is caused by this apocentric pileup, by these stars from the Gaia Enceladus sausage that pile up at these apocenters and then cause this observed break in the density. Now, another interesting thought is that because of the accretion event, we think that this happened once there was already a sort of puffy disk in the Milky Way, and we think that this accretion event might have heated a disk population onto what some people call the in situ halo, some people call the splash, some people call the heated disk or primordial disk. But essentially is that you have an impact, and then the impact drives sort of heating in the disk to these more radial-like in situ populations. So this is another interesting aftermath of that we think happened because of the merger. However, as I was mentioning before, there's a bunch of other substructures that have been identified, and primarily they've been done using diagrams like this. So this is the orbital energy and angular momentum plane. And it's just computed using the astrometry and the radial velocities. So you get kinematics, and then given a potential, you get orbits. And here's a result from some work that I led, just showing how there's different populations that people have identified. And actually, if you take all these populations and select them by the means that people have done so in the past, because we have amazing spectroscopic data now as well, primarily from Apogee, we can also go on to study their chemical abundances. And this, I think, is really powerful because you're doing a kinematic or dynamical selection and then looking at the chemistry to try and understand more the origin and the reality of these different stellar populations. So here you have the alpha ion plane, where we use magnesium as the alpha element. And you can see how different substructures occupy different parts in this plane, right? Highlighted with the colored markers. Now in the background you have the alpha bimodality, which is this double sequence of fixed metallicity that the Milky Way disk exhibits, but I won't go into that. I'll just focus on the halo populations here. So it's interesting to see that some populations show like a sort of plateau and then it truncates. Some populations show like a knee going down, like the Gaia Enceladus sausage. Others present an upside down knee, and others occupy different regions in the diagram. Interestingly, two halo populations, conjectured to be debris from accretion events, actually overlap in chemistry with the disk. So for example, Aleph and Nix, which actually implies that these populations are likely formed in situ, but have somehow ended up on orbits that resemble more the stellar halo. So again, going back to this idea of either a heated disk or some sort of heating mechanism that drives in situ stars to not have in situ dynamics. But essentially what we did was we took this and then looked at all the different elements that Apogee provides and compared them both statistically and qualitatively to try and assess the reality and nature of different stellar populations. And I think this is really powerful, the synergy between dynamics and chemistry. And in doing so, it allowed us to really try and constrain, as I mentioned, the origin of these populations and in their nature, but in turn, the accretion history of the galaxy. So in the study, we kind of hypothesized that the Milky Way, from what we know and what we can observe so far, has likely had two major mergers and then a bunch of many smaller ones. And this is actually what you'd expect from cosmological simulations as well. Now, the interesting thing, I think, is that is trying to understand where you'd expect different mergers of different masses that infall at different times, and how they are then spatially distributed in the Milky Way to then go and hunt for them, to try and understand how many building blocks it took to form the galaxy. So to answer this question, some collaborators and I looked at the fire simulations, and what we did was we took 7 Milky Way mass halos and then tracked all their accretion events over time. And then we we classified them based on the time in which they infall and then their stellar mass. And if you plot their present day average galactocentric radius, you see this stratification whereby smaller mass systems tend to be either very old or very far away. And at fixed infall time, more massive things get pushed deeper into the potential of the host compared to lower mass things. So this leads to this stratification in mass. Now, overplotted here are some lines where you'd expect Gaia to be able to observe both RGB stars or main sequence terminal stars. And then on the top, you can see how LSST is actually going to just drive this out of the park, right? Because we're going to probe really deep and faint regions of the stellar halo. We'll be able to capture the majority of the debris from these different building blocks. So I think this is one of the things, one of the predictions that LSST will be really insightful for. You'll be able to really probe the distant regions, and from that we'll be able to try and understand these smaller mass building blocks to get a sort of a mass function of accretion events in Milky Way mass galaxies. Interestingly, as I said before, the chemistry is also quite important because it tells you, it gives you a lot of information about star formation history, which is obviously linked to the time in which a system forms, but also how massive it is. And looking at the alpha ion plane, you can see how in these simulations there's a stratification also in mass and in infall time. So if we are also able to measure alpha and ion abundances, we'll be able to then piece together or have a better insight into the somewhat approximate measurement of the mass and the time in which the system infell. Now, another thing that I think is interesting from the chemistry is that I've been talking to you about the alpha ion plane, but actually alpha elements, which are somewhat relatively straightforward to measure from spectra, not all of them are produced in the same way. And actually, if you look at the main two subgroups of what people call the hydrostatic and the explosive elements, alpha elements, you can use the ratio of the two to try and infer a sort of proxy for the high mass end of the IMF, so the initial mass function. And this is because the hydrostatic elements, like magnesium and oxygen, are produced in the cores of the most massive stars, so 30 solar masses or above. However, the explosive elements are produced during the actual supernova type 2 detonation. So therefore, if you have a measurement of both, you can get a ratio of the most massive stars to all supernovae. And this is what I'm showing you on the right here for stars in dwarf galaxies, in triangles, in globular clusters, and in halo substructures. So then you can compare these to try and see how many massive stars essentially contributed to the star formation history of these different systems. And interestingly, you can see that present-day dwarf galaxies have a lower ratio at fixed metallicity compared to things that are formed in the earlier universe, like globular clusters or halo substructures. So I think it'd be really interesting if we can get alpha elements for these distant halos populations to try and contrast the different types as well. Now, in addition to all the phase mix things, there's also a bunch of kinematically coherent things like stellar streams and disrupting or infalling dwarf galaxies like the Sagittarius Toroidal or the LMC and the SMC. And there's been a lot of work trying to understand stellar streams, and this is because they're interesting not just from an accretion history point of view, but also from a dynamical point of view, because they give you information of the profile of the stellar halo, dark matter, and all these different kind of things. And we now have observations for many of these. One of the most prominent ones, of course, is the Sagittarius Toroidal stellar stream, which expands, it wraps around the whole Milky Way, even a couple of times. So therefore, it's this prominent structure that we can really use to model sort of dynamically the properties of the halo of the galaxy and so on. But in addition, we can also look at the chemistry, as shown on the right here. And of course, in addition to this, there's also the role that infalling satellites have on disturbing the potential of the host. So there's been a lot of work in recent years trying to understand how considerably big satellites like the LMC and the SMC perturb the halo of the host and shake it up essentially. So you have this sort of wake and response that is due to dynamical friction. And of course, this happens for satellites that are somewhat close in their pericentric passage. But it'd be interesting as well to see if other things that we can find further out, or if we look, for example, at Andromeda, and we know that it has the giant stellar stream and M33 and so on, how these affect the profiles of stellar halos and how we measure properties. Now, in addition to individual accretion events and their role in the buildup of galaxies, there's also been a lot of work that dates back even to earlier work trying to understand the global properties of stellar halos. And by that I mean the density, so the profile, the stellar mass, how much mass there is, and also the shape. So when modeling the stellar density, there's been a lot of work that has done this, and initially was conjectured to be a power law, and then it went into a broken power law because of this apocentric pileup. But as more and more work and more data has become available, there's been more and more proposals for this sort of density profile of the halo. But I think we can sort of agree on an oblate profile essentially for at least the inner 30 kbc. So we think that it's squashed, and it's likely due to the debris from the Gaian-Sladder sausage because it dominates the local stellar halo, and we think that it breaks around 20-30 kbc, and that its power law is I think roughly in the order of minus 1.5 to 2 in exponent. Now, if you integrate this density, you get a mass which amounts to approximately 1 to 1.4 times 10 to the 9 solar masses, which, as I mentioned, is about 1% of the total stellar mass of the Milky Way. However, this number seems to be growing and growing the further out we can go and the further in we can go as well, towards the innermost regions of the galaxy. And there's different ways that people have done this. And of course, in addition to the profile and the mass, also the shape. So how flattened or how prolate the stellar halo is, which can give you indications of both the accretion history, but also the role of dark matter and how it shapes stellar halos. And lastly, I'd just like to re-mention here that in addition to all the accreting material, of course, we have all the in situ material that forms stellar halos. And there's been a lot of work doing this, both from the simulations and point of view, but also more recently with the advent of this amazing data, a lot of work doing more on the model and the data side. And this is in a multifaceted approach, again, using kinematics, chemistry, and if possible, ages as well. And I think the verdict is still kind of out on how much in situ stellar halo mass there is and at what radius and where it dominates, but we know that it is there, and we know that it must have formed somehow, right? So I think that'd be something interesting to look at with LSST, for example. How far out do we think the in situ halo goes, and at what radius is it really dominant? So just to wrap up there, I've listed here a bunch of different thoughts that came to mind on how Rubin LSST will help understand more both the formation of halos and stellar halos, but also the role they have in the buildup of galaxies like our own. So some of the things that I kind of thought would be really helpful would be LSST, because it's going to go so deep and so faint, we'll be able to search for the faintest satellites and stars in the Milky Way and local group. Of course, we'll be able to measure kinematic properties, but I think also chemical properties, if I'm not mistaken, of the most distant halo stars, allowing us to probe the outermost substructure and of course, dark matter. As I just mentioned, I think one of the questions that I find interesting is how far does the in situ halo go and how much does it contribute in mass? You'll be able to model in incredible detail the Sagittarius Phosphoridal and other stellar streams and shells and so on. And I think you'll be able to really push the measurements that we've been making, these classical measurements of the density and the mass and so on, to really far out regions. And of course, there's also, in addition to all the field populations, a whole other field of research, which is globular clusters, which I've not had time to talk about, but you'll be able to learn a lot of things about those as well. So at this point, I wanted to kind of open up the floor for discussion, and maybe we can chat about how LSST is going to be awesome and how LSST is really going to be able to contribute to all these different probes In my mind, they fall into the realm of understanding dark matter, understanding stellar halos and the accretion histories of galaxies, and then how they've influenced the role and build-up of galaxies and evolution. But maybe you have further thoughts that I've not been able to list here. So thank you for listening.
Thanks. Yeah, very nice talk, and it's super interesting. Yeah, a review of the local group to some extent. So for questions and comments for anybody, when you use raise hand, I can yeah give you right. Yeah. Let's go. So the first one is also coming from me. I want to could you come back the energy and angular momentum of the panel?
Yeah.
Just now I think the fifth or sixth is or yeah.
This one.
Here, yeah, this you can see the how to say the sign points. We can see it's very dispersed on the right panel, and on the top right, top left. Yeah, we can see the sign points. It's Arjuna. It's very
Yeah.
dispersed. I'm very curious how what happened here. You can see there. Yeah, it's very dispersed. Yeah.
Yeah, it's a good question. I mean, so just a bit of context. So Arjuna and then ETOI, and there's another one, which one of the sequoias is a group that, so the H3 survey, it's a survey from Harvard that happened in the early, I think it was 2020, and they had this paper led by Rohan Naidu, where they sort of try to understand the stellar halo, right? And in the high energy retrograde space, they sort of divided it into three populations. So what they did was they selected all the high energy retrograde stars. So they made a box like this. And then what they did was they looked at the metallicity distribution function and they found three peaks. And then what they did was they assigned stars to each peak. So I think that's why you end up with a very dispersed region there. But as I showed in this plot, oh no, that's Aleph, never mind. But I think what's happening here more likely is that Arjuna is not really, in my opinion, the debris from a separate event. I think this is the tail, the high energy retrograde tail of the Gaia Enceladus sausage.
See,
This is because if you look at the chemistry, it's basically indistinguishable. And
yeah,
you can do this statistically as well.
yeah.
So I think that's why it looks so dispersed, right? So you'd expect stars at high energies to disperse in angular momentum as well.
Yeah, some people claim then the Arjuna or some others, yeah, all from the GC, right? I think
Yeah.
I'm not sure you are the co-author. The Charlie Conroy is Rohan Nadu's paper.
Yes. So they find them, right? And then we looked at the chemistry, and I think a lot of them are likely part of the different overdensities of the same debris. Yeah.
Yeah. Okay. For the next page, the chemical pattern, I think we can see the for Sagittarius, the magnesium is very low,
Yeah.
but for the gas sausage and the sequoia, we can see the alpha abundance, the magnesium is higher. Yeah, which makes me a bit yeah confused how to see how to understand this Sagittarius of galaxies has a very low magnesium.
Yeah, so the way we think that, so Sagittarius being something that accreted much later, can reach, by default, can reach higher metallicities. Now, but if your star formation history or star formation efficiency is lower, meaning that you don't have as many
But it has right. It has some star formation.
Well, it definitely does have star formation, right?
Yeah,
Otherwise,
it has
would it
star
be
formation,
star?
but it's just no. I guess compared to the gas sausage or
Exactly. So you
yeah.
have a lower star formation efficiency, which means that you can reach higher metallicities, but at lower alpha over iron.
So or how about the range of the location of this substructures, or are in the local here, right?
So
Or no, no. The range.
Enceladus is, but Sagittarius is, I mean, between 20 to 30 kpc we're talking.
I know. I mean here the samples location and samples range.
Yes, that so the distance ranges up to 30 kpc. So from the galactic center, it would
Mm.
be anywhere from 0 to around 30 for all the substructures. For each individual one, I don't know. I'd have to check.
So the distance is around the 0 to 30 kbc. The
Yeah,
distance.
yeah.
But you know when we go farther, when we go farther in the outskirts, the mechanicity should be lower. The mechanicity should be lower.
In
So
theory.
is it suitable for us to use the cut of the chemistry about the minus h, minus point h, minus point h, minus point 7 to separate the populations of the accretion?
Well, I guess this goes back to the question of where does the in situ halo finish,
Mm.
right? I think to a first degree you should be able to, right? You can make a cut -8 or -7 or -1 or whatever you want. And you should remove most of the disk and in situ things. But there's also the question of where does the in situ halo stop, both in terms of the distance and the chemistry. So I guess yes, but if you take that into account, then maybe not so yes.
Yeah. Okay, for ours, do you have any other questions from the audience? I noticed some people has left, but
Maybe one thing I would ask is what are people most excited about with LSST for the stellar halo and the near field cosmology questions?
yes, yeah. I'm not sure the 陈叶潮. Do you want to show your interest about the LSST? 陈叶, do you have any expectations for LSST science? This is yeah, informal talk and discussion, so feel free. Yeah. I noticed he has unmuted, but he didn't say anything. You want to say?
Yeah, yeah. I mean, it doesn't have to be now either, right? We have the Slack and we have the document as well that we can exchange ideas on.
Yes, yes.
But
For me, for the area SST, I'm very interested in this all these topics, but I think the key question, one of the key questions for these topics is that how precise we can determine the photometric distance, photometric mechanicity, and photometric a lot of our photometry. Photometry is very accurate, and the proportion, I think. Do you have any
mm,
ideas? We could organize some ways to determine the distance and mechanicity of the areas. Then we can do this, right?
mm,
Yeah, yeah.
right.
I'm very curious. I cared about the creation history of the dwarf galaxy and the globular clusters. Yeah. Oh, yeah. So,
Sure.
and I think the area system could go to the how to say the very yeah the very fate. I think the limit magnitude should be much better than the Gaia. So the dwarf
Right.
galaxies and some globular clusters should be coming. And with the catalog of the group clusters and the dwarf galaxies with the mechanicity and with the distance and per promotion. And we can do something. Yeah,
Sure.
we can do many things. Although
Nice.
we don't have the radio velocity. The radio velocity is still lacking. Do you have any ideas? I don't know. I don't know which survey WSST is in the future. The radio
Right.
velocity is still ranking because our group often use the per promotion
Yeah.
to do something, but we don't have the radio velocities. So yeah,
So
yeah.
there's
Anyway,
a, I think there's a few. I don't know how far out we're talking about here, but there's a few surveys. So I know, like, for example, in the north, PFS is looking at the Andromeda system. So if it's looking at the Andromeda system, it should be able to get out to the distant regions of the halo.
Mm.
So that could be one maybe that you could use synergies of. Um, there's Foremost and Weave, of course, like the low resolution arms of those coming online. So maybe those will be helpful. But I don't think there's a plan for a big spectroscopic campaign to match LSST, if you know what I mean, which
Mm.
would be amazing, right? But like,
Yeah.
yeah, it's a lot of time and a lot of money, so I don't know.
Yeah, and another thing is that I'm also interested in the star formation. The star
Hmm.
formation and internal dynamics of the dwarfs and
Yeah,
the orb clusters. Yeah, I think you condition on the color diagram and some tools we can start something about the star formation. Just
definitely.
use the photometry information.
Yeah,
Yeah, yeah.
yeah. And remind me, so LSST is going to observe in which bands of how many bands of photometry is it?
Yeah. I'm not sure. I'm not sure.
Oh, okay. So,
I'm not sure.
'cause, yeah, if you have,
Because we only have so far they just showed me some papers using DP1 data preview area 60. Yeah, so I'm not sure the details. Kristen is not here. She might know, but yeah, but anyway, I will check with her. Yeah, yeah.
I think there's,
Mm,
I think there's a few. It's like seven or eight. So
mm,
there's a bunch of stuff you can do there, right? But yeah, I mean, for specific traces as well, just because you're gonna have shit like the amount of number, like for precise measurements for the distances, for example, like the RL Lyrae or the red clump stars or the
yes.
tip of the giant branch, right?
Yeah,
Those
yeah,
kind of stars, you're just gonna have so many. You
yeah.
still have good numbers, even just restricting yourself to
Mhm,
those sort of regions of the of the CMD.
yeah.
I
Yes.
think will be good.
Mm. By the way, in your finger, how do you define the info time? In your finger, I don't
Oh, in the
your info time
simulations,
is
yeah. No, that's a good
very
question.
complicated. This finger, yeah.
Yeah, people define it in different ways. In the simulations, what we did was we
Mm.
defined it as the point in which the subhalo crosses the virial radius of the host.
Wave readers, you mean?
Virial radius, yes.
But yeah, sometimes I think I'm not sure. Some people define it and it's Apple center distance.
Uh,
Maybe
well, it'd be like the first apocentric distance, right?
yeah for the first Apple center, yeah.
Yeah, I mean that's the same, I guess, as like once it's bound, right? And in order to be bound, you need to be inside the virial radius. So
Mhm,
as soon as you cross the virial radius, you're bound, and that's your first apocenter, right? So I guess it's the same definition.
mhm.
But yeah, it's a tricky one because people define it in like I don't know once it like impacts or like different things. Um, but we defined it as
Mm.
the time in which it crosses the virial radius of the host. Exactly.
Yeah. Yes. Yeah.
Yeah.
Yes. Yeah. For any other questions for the audience, yeah, we will control the meeting time within 1 hour. Yeah, if you want to ask something, we still have around 5 or 10 minutes. Yeah. 关于 do you want to ask something? I and Guanyu developed a method called the G3 Hunter to search the streams these years. By the way, we have some new things and about the gas sausage in cylinders. We find so many, how to say, the peaks and in the chemical patterns. So,
Oh,
so
really?
so maybe I remember you asked a question to the audience in the EAS. Yeah, do you believe the gas sausage is truly younger, right? Right.
Yeah.
You ask a question. Anyway, yeah. So far we are far from the answer, but I think the structure is more complex because we find there are so many substructures in the GSC stars. We are writing the paper. Yeah.
Okay.
The chemical pattern means then the aluminum and the magnesium and some also oxygen.
Uh-huh.
And we find there are so many small clumps small clumps in the substructures. We find four substructures in the four or six. Yeah, so you are the co-author of the Heidi Newberg's group, right?
Yes, the
Hades
one.
paper.
Yeah,
Hades.
Tom Long.
I had a discussion with Hades. Yeah,
Okay.
she showed she showed the results of the gas sausage. So it seems then that it is still under discussion, right?
I
Yeah.
think so. I think so. I mean, it depends who you talk to, right? But
Mm,
there's some people that are very adamant it's one thing. But I
mm,
think that the possibility of it being multiple substructures, varying in age and in, mass, um, is definitely a possibility. It's definitely a possibility. I still think that there has to be some more dominant thing, but I think within the whole debris, there could be like smaller things within it, right?
mm.
Um, yeah, definitely. But that's interesting. Okay, so you find multiple
Which one do you prefer, in your opinion? I think you prefer the younger one, right?
No,
Which one
so
do you
I don't prefer anything. I just
I
I
know.
would just like to know, you know? I
I
think
know. Uh,
I think from the data and the evidence that I've seen, I would say there's likely debris from one big thing, although I don't think it's as big as people claim it is.
mm,
It's still big, but not as big. And
mhm,
then I think within that, there's some smaller things that could be younger, could be smaller, and so on.
mm.
Yeah.
Yeah, yeah,
But
yes.
that's my interpretation. I don't know. I don't know if you agree or if you think that it's many different things, and I don't know.
Yeah, maybe when I finish writing the paper, we could have
Right.
a discussion.
Yeah, it'd be interesting.
I will send you for the discussion. Yeah, both you
Yeah, yeah.
and yeah.
Sounds good. I'd be interested to see that. Yeah.
Mm.
So, which is this Apogee data then that you're using, or
We
is
use
it
Daisy.
DESI?
Yeah,
Nice.
yeah.
Okay.
This data and
Hmm.
also apogee. Yeah, yeah.
Nice.
We still have some tests. For the data we have four groups, four streams for the gas sausages sample, for apogee we even detect some six clumps, six streams of the in the gas sausages sample. So it's a bit strange, but it's very interesting. So
Very interesting. Very
I want to write
interesting.
a paper. Yeah, we are writing. Yeah, it's yeah. Mm.
Okay.
See,
Because
yeah,
then, if it is a bunch of smaller things,
yeah,
then that whole argument that
mm,
the halo is just one big thing breaks down, right? Like it has, like that is okay. That's cool.
yeah.
Yeah, let me know when it comes out because I'll be interested in reading that.
Yeah, so far I often use we cared mainly about the the north side, the north sphere, because we are in China we have the most data survey. We
Sure,
don't
sure.
care too much about the north survey and the north yeah, skies. So we with the help of the LSST, yeah, for myself I'm so eager to head to the south hemisphere for the dwarf galaxies and the globe clusters and the near field cosmologies. I think all
Hmm.
guys here is all are interested. Yeah, such like the Rigor and the yeah
Yeah,
and others. Yeah, yeah. Mm,
awesome. No,
yeah.
yeah, I mean the South has all the beautiful dwarfs, right?
Mm,
And it has some cool streams and global clusters that you can't see in the North, so that'd be really interesting.
yeah,
Because
yeah,
I guess you'll see with LSST, you'll see Omega Sen like incredibly well, right?
yeah, yeah.
Yeah,
Yes, I agree.
the beast. Yeah, no,
Mm,
that'd be really cool. Yeah, nice,
mm.
nice.
Okay. Do you have any other have questions? If no more, I think yeah, and yeah, thanks for your coming and thanks for yeah to be
Thanks
here.
for having me.
So many insightful yeah, insightful
Lovely.
sites yeah, and
No,
I
it's been
have
great.
made a recording and I will make it public on different platforms such like YouTube and in China we have the Bini and we also
Okay.
have some others. I will make it public after this meeting. Yeah, we
All
were
right. Thank you. Yeah. Do
just
send me the link to the recording as well if that's
yeah,
possible.
sure. Yeah, yeah. First, yeah, because you are the first speaker. You are the first speaker. Yeah, when I became the co-chair of this group, so
Privilege. Yeah. Wow.
so
Thank you. So
so
kind.
yes, yeah, and I know, yeah, and I congratulations for your marriage of the yeah.
Thank you. Appreciate that.
Yes,
Thank
yes,
you very much.
yes, yeah,
No, it's been a pleasure. Thank you for the invite, and yeah,
yeah,
if you have any more questions, reach out. But if not,
yeah.
thank you.
Yes. Yeah. Okay. Thank you. And so, okay, let's finish this meeting today, and we will have another meeting, or our second meeting is in September. Yeah. Another girl in Canada will share some also insights about the near field cosmology. I guess. Yeah. Okay. Yeah. If no more comments or if no more voice, I think we could see you next time in person or online. Yeah. Okay. Many thanks again to Danny. Ciao.
Thank you.
Bye
Bye.
bye.